Hello and welcome to another Carbon tutorial in Maya. This time we will be having a closer look at the Carbon simulation node. We will be going through most of the parameters on the Carbon simulation node in this video. I would also recommend maybe opening the reference documentation on the side so you can read more information on each parameter as well that is in the reference documentation that I might not mention in this video. So let's get started. The Carbon simulation node can be found on the Carbon shelf here all the way to the left, or if you go to the Carbon menu, it is right here under Open Documentation. So let's create a Carbon simulation node. The first thing you probably now notice is that there's only one type of Carbon simulation. Yes, that's correct. We only have one type of simulation, which means all of the Carbon objects and constraints are all part of the same simulation. So you have cloth, colliders, more of rigid bodies, you have all the constraints, and in Houdini you have feathers, you have tissue and tetrahedrons. All of it is part of one simulation. So everything interacts with each other in the same simulation. There are no separate stages. Everything collides with everything per default. And if you want something to not collide, then you have nodes like the Carbon filter and Carbon narrow filter, where you can disable collision between pairs of objects. So now let's have a look at the Carbon simulation and its parameters. For this, I will bring up a scene so we can see the effect of some of these parameters. Here is the cloth.mb scene from the documentation. And now we can start going through the parameters. In the general section, the first thing you will find is the deactivate button. This simply deactivates and activates the simulation. Well, you might want to deactivate the simulation if you have multiple simulations and you want to switch between them, or maybe you need to go across in the timeline and set some keyframes, and deactivating makes it faster so you can just go and you do not have the simulation running in the background. Because when I activate it again, the simulation will now run and simulate up to this point. Okay, here we are. It is now simulated to frame 102. Next up is the physics draw. The physics draw is a draw mode that allows you to see what the physics solver sees. So for example, when you go on the meshes here, with the physics draw enabled, you see the actual thickness that is set up in the cloths. If I hide the physics draw, you will see the output meshes, and these are thin meshes. They do not have the physics properties displayed on them, so you can't really tell how thick they are. We generally recommend turning on the physics draw so you can easily spot issues. For example, accidentally setting the thickness 10 times as thick or 10 times as thin. The next parameter is called show type draw, and this is very simple and very rudimentary at the moment. When you enable it, the only thing it does is displays the simulation text where the Carbon simulation is. So if you were to change the simulation position, for example here down there in the simulation space, which we'll talk about later, the text will show up now on location 2, which is up here. That's all about it. So let's just disable it again, because usually I do not want to see it. Next up, hide debug messages, and this refers to all of the messages that you can find in the script editor. The script editor is here. I'm gonna go, let's say, to the first frame, reset the simulation. You see all of these outputs from the Carbon simulation. You click this, and if I reset now, you only see a reset, but you do not see the time. And if I start simulating, you do not get all of these messages about the frame times. So if you want to reduce the output messages, you toggle this button, but I like to turn it on. And here we are. Next up is start frame. The start frame by default is 1 because most things start at 1. But if you want the simulation to start in a different frame, you can change this. For example, I've set this to 10. Let's reset the simulation. And now we step forward. It starts at 10 and I was already on frame 10, but here nothing happens before frame 10. You can see. Now let's set it to a different frame. Oops, it's simulating. Press escape to cancel, which is, by the way, a good thing to know. Press escape on your keyboard and hold it to cancel. So let's set start frame to 100 and reset simulation. It will automatically bring the timeline to 100. Nothing happens before 100, but once we go past 100, it starts simulating. Next up, step. This marks the step in the time frame for which a simulation is triggered. So 1 means for every one step in the timeline, we're going to simulate 1 frame. Now I'm going to bring up the debug messages again here. Let's just clear this out for a second, and here we are. All right, so if I go a frame, we get another simulation update. Let's go back to the first frame, reset the simulation, set the step to 0.25. So now reset the simulation, and if I step forward now, we're moving 1 frame here in the timeline, but our simulation step is 0.25, so we actually simulate 4 frames. And usually you want this feature when you actually have a timeline with substep as well. So your setting in Maya could be a substep setting. If I change this to 0.1, we would simulate it, obviously 10 frames per time step. Go back to frame 1, reset simulation, go forward, and here we are. We have 0.1, sorry, 1.1, 1.2, and so on, all the way up to 3. So we have 10 simulation steps happening. Next up, frame jump limit. This is one of the newest features, and this allows you to enable a limit as to how far along you can jump in the timeline. Let me enable this, and here the limit is 100. Reset the simulation. So if I was to jump to frame, for example, 6, you can see that it simulates all the way to frame 6. Now, if I click on a frame larger than 100, for example, 102 up here, you will see it says large jump detected, stopping simulation at frame 1. This is very useful if you accidentally save your scene, let's say at frame 1000, and when you load it up, you not want it to simulate all of the frames leading to 1000. So if this is something that happens to you quite often, you might want to consider enabling frame jump limit. By default, it's disabled, so let's revert that. Next up, allow automatic resets. When this is ticked and is ticked on default, then changing some of the parameters will automatically reset the simulation. Let me show you. I'm changing the start frame from 1 to 2. And our simulation has reset. Now change the start frame back to 1. Our simulation has been reset. Let me untick this now. And I'm going to change it to 2. And nothing happens. Change it to 10. Nothing happens. You will have to manually click reset simulation for this to come into effect. This can be quite useful if you tend to make a lot of changes and do not want to have the simulation reset all the time. So for example, if you make a lot of changes to different nodes like cloths and colliders, any simulation node, and you do not want every time a simulation reset to happen, you turn this off and then you only manually reset the simulation. Obviously, this means that you have to remember to reset your simulation after you made the changes, because otherwise they will not come into effect immediately. Next section is the simulation cache. Per default, Carbon has its own simulation cache, which stores the physics states. So if I play here now, and I'm going to scrub around, this is replaying from the simulation cache. If you have the simulation cache on, you can do this. Without the simulation cache, obviously you cannot scrub and will be stuck on the last simulated frame. So let me turn this one off. Reset the simulation, and we're going here, let's say to frame 14, 16, and so on. If I now scrub back, you will see nothing happens. It is because we do not have the simulation cache on. So you might want to turn the simulation cache off if you have a very large scene for a lot of high resolution geometry, because obviously storing the cache internally takes up more memory. If you have a machine with not a lot of memory, or you do not need to actually play it back because let's say you're saving out the results on the fly, you can turn simulation cache off. Next up, simulation cache, restore messages. Again, let me reset the simulation. Actually, let's change back to frame 1 because that's much neater. All right. I'm going to go now to frame 11, and if I bring up our script editor, we have the first few frames simulated here. And when I scrub, you do not get a big message besides the Maya message I changed something the time. If I click the show cache restore debug messages, then when I change the frame, I additionally get the message from Carbon saying that an internal cache has been restored. Usually this just floods your script editor quite a lot, especially if you scrub a lot, so I would just keep it off. Next option is to integrate with the Cached Playback. Newer versions of Maya have a Cached Playback function built in. So if you go down here and you can turn on the Cached Playback toggle, what this will do is automatically trigger a simulation because all of the frames are supposed to go into the Maya Cached Playback. So Maya tells Carbon we need all of these frames to be evaluated, and Carbon will then evaluate all the frames and simulate up to this point. There we go. So now all of this has happened. When you click integrate with Cached Playback, for example, if this is ticked, editing non-keyframe parameters will result in a full reset, even if the parameters do not affect the simulation, such as the debug message tick boxes or the physics draw. So if I show and hide the physics draw here, per default, it will not trigger a simulation reset. But if you have integrate with Cached Playbacks turned on, changing the status of the physics draw will trigger a full resimulation. Next up, reset frame. This allows you to reset the simulation to something that's larger than the start frame. For example, here we have our simulation gone all the way to frame 92. If I change my reset frame to, for example, 50, do a partial simulation reset. So now if I click it, I'm back on frame 50. Everything before is still there, but after 50, it starts re-simulating. Another thing to mention here in the simulation cache section is the cache import and export subsection. By default, it's collapsed, but let's open it up. Now here we see there are two parts, import and export. And you have a tick box to show some of the dialogues in your script editor. I'm gonna run my simulation. And now I want to export my simulation to cache. I need to obviously first point to a folder, and I got one here, cache. And I'm gonna select this folder and accept. And now my folder is in here. And I need to set the cache file name. Let's just keep it carbon simulation shape 1. If I press export now, it will try to export all existing frames in the carbon simulation cache, which are frames 1 to 47. So let's press this. And it asks, do I want to do this? And asks if I want to overwrite any existing files. And you'd say yes. And here you get the message saying exporting all current cache frames, frame 1 to 47, and it was successful. Perfect. So now we can also import them. So I'm going to disable this now. Import. Nothing currently import here. So let's figure it out. And we want to point to the first frame. So it's labeled carbon simulation shape 1. That was the name underscore and then our frame numbers. You want to pick the first frame and say how many frames you want to load in. So if I go to 2 and let's say reset the simulation, it will now try to import from cache because I have enabled simulation cache import ticked. Let's show the script editor, and we can see down here, import cache load successfully, loading frames 1 to 2. If I change to 20, for example, and I reset my simulation again, now it will show 1 to 20. And if we go now and go ahead here in the time frame, we go up to frame 20, and then it's going to start simulating. And if I show the script editor again, you can see this. We stepped up to frame 20. Nothing was displayed because we do not have the show cache restore debug message. It's on. But once we hit 21, it started simulating because we do not have that right now in cache. Now, if you go to enable simulation cache export again, it's going to ask you again, confirm, and it's going to export all current frames, which is up to 25. If you go to reset simulation and you have enable simulation cache export ticked, it will export them on the fly. So if I run this now, it's going to export all of the frames as they're being simulated. All right, you can see all of these frames are simulated. I can untick this and let's try to reset the simulation, import more frames. We're up to 100 frame 79. Oops, sorry, 179. Let's reset the simulation. And we can see successfully loaded frames 1 to 179, and I can scrub here and nothing happens. And when we go after 179, you can see it starts simulating again. And now we simulated the whole timeline. If I click export, it's going to do the whole batch. And we have exported 1 to 200, which you can see here in the script editor and in the status message. Now, one thing also is to keep in mind that the end frame here does not necessarily have to match what you have. So if I set the end frame here to 2000, for example, which is way above what we have, and I try to reset the simulation, what you can see here is an error saying that 201 doesn't exist, and it only loads all valid up to this point, so 1 to 200. So if you're not quite sure what the end frame is, you can set it to something large and will just load everything that it can find. Also, one thing to note is if you have substeps enabled up here, your simulation will also export the substeps. So let's change this to 0.25, reset the simulation, and the first thing you can see now is that it tried to import because we have import ticked, but 1.25 is not existing yet because we didn't simulate with substeps before. So let's simulate for a bit. And we can obviously get the messages from the simulation output, and export was ticked, so everything after this point has been exported. Let me untick this now. Let's try to reset the simulation. We still have import ticked, reset, and it imported everything up to frame 75.25. So let's go forward. We can see after 75.25, here it starts simulating. One other thing to note is that you do not have to actually have the simulation cache ticked on the simulation in order to export. So let me untick import, let me untick use simulation cache. And then what you obviously need to do is you need to enable export from the beginning, because if you simulate some frames here, let's say, let me reset. We go up to frame 70 here, roughly. There we go, 71. When you click export now, What it does, it tells you it exports the first frame, but actually it exports only this frame. Because the cache says there's basically nothing in it, we're empty, and it just tries to export the current frame, and we're up here. So this doesn't make any sense. What you need to do is when you have simulation cache disabled, you go to the first frame, make sure you have enabled simulation cache export on, reset the simulation, and then if you press now, it will export on the fly as it goes along. So obviously export can be very useful if you want to replay the simulation afterwards. Also, there's a difference between a cache export and, let's say, if you exported your whole scene as Alembics, because the simulation cache contains more information than just the geometry. It contains internal states, velocities, and so on, so data that the physics solver needs to continue simulating. It can also be very useful that if you want to simulate a long scene, and you might want to make some changes halfway through because you get some behavior you don't like, but you like the first 100 frames. So why not save out the first 100 frames and then keep imports on and set to 100 frames. So it will always load the first 100 frames into cache, and after that you can make changes to the parameters and simulate on. Lead simulation. We have a lead simulation example, which I will just bring up quickly. Lead simulation runs an optimized simulation interpolating between the start and the reference metrics of all objects and all constraints. So for example here, cloth and binding. What it does, it allows you to go in one frame from something like this, for example, to something like this. It's an optimized version, so it should be faster and happening under the hood. You do not have to actually store the intermediate results. There are two options. First of all, duration, and second, stasis mode. Duration says the virtual timeline of how many seconds should be simulated. For example, at 24 FPS, that means half a second would be half 24, so would be the equivalent of 12 frames being simulated in just one frame. Stasis mode. Stasis mode triggers a dynamics integration that ignores all action forces and wipes out all kinetic energy, reducing motion and deformation to only results from the reaction forces generated by constraints such as collision, joints, or soft primitives. In practice, every dynamic object feels like it's in clay that can be sculpted. So for example, this turns off gravity, or if one thing knocks another one, it's not going to keep moving. It just basically stops as soon as the collision is done. So you can either tick it on or off. It depends on whether, for example, you want things to fall down. So here, if let's do it again, reset, step forward a frame, I have my straps on the shoulder fall down. If I now tick stasis mode, reset, they might not fall down depending on how the cloth behaves. See, here now they are hanging here because stasis mode doesn't take gravity into account. Now I need to simulate a couple more frames for it to settle. There we go. While if we look at this again and I disable stasis mode, reset the simulation, run a frame, and it has come in much nicer because gravity has already been taken into account. Next up, gravity. Per default, the gravity is set in bidirection to minus 9.81, and this is meters per second square, which is the gravity we find on our planet Earth. Obviously, if I simulate this now, you get results that you would expect. And if I reduce the gravity to, let's say, -1 only, then what we get is gravity that's much lower, which you would find on some other planet in our solar system, for example. And if you set gravity to something positive, like 1, well, no surprise here, it's going to go up. Next up, air density. Air density is measured in kilogram per cube meter. 1.204 is the value for air density at sea level for 20 degrees Celsius. If you reset the simulation and run this, you should see a normal behavior, and actually air density is not being taken into account. This is because per default Carbon simulates everything in a vacuum. There is no air interaction. In order to actually turn on any interaction with air, we need to do two things. Number one, we need to add a Carbon flow node. Set this to a uniform field with no movement. So this activated now having air in the scene. And next up, in order for the cloth to interact with it, we need to set aerodynamics parameters. I'm just going to change form drag to 1. Let's go now to our simulation, reset the simulation and run. And we can already see this has slowed down a lot. If we increase air density even further, let's say to 10, we should see a further slowdown. Increasing air density is saying that your cloth is now in a different volume, so heavier air or maybe water or honey, so in a more viscous fluid. And this slows down all kind of behavior and makes things just go much slower. If you have a character with garments on it, for example, a long dress, and you increase the air density, as we did in this example, it should start lagging way more behind. It's like walking underwater. Next up, iterations and subdivisions, and we really need to talk about them in one block together because they both affect the convergence of the solver. The carbon solver is an iterative solver, meaning that during each simulated frame, it will run a fixed number of iterations towards the correct physical solution. The larger the constraints network, so meaning the more triangles and the more quads you have in your mesh, the longer it will take any iterative solver to reach a converged state. That also means that with a fixed number of iterations and subdivisions, you will almost never reach the converged state because most problems are too large. So in practice, that means when you have more triangles or more quads in your simulation, you need more iterations and more subdivisions to get close to conversions for your specific problem. When you have just a small number of triangles, you need much less iterations and subdivisions. So therefore, one thing to keep in mind is that you should only use as many triangles and quads as you actually need to resolve your material. So if you have a leathery garment, you don't need that many triangles and quads as you would for a silky garment because the folds in the leather are much larger than in the silk and can therefore be represented by less triangles. Less triangles means you need less iteration and subdivision towards convergence, and both together means you're going to run much faster. So a silk simulation will typically run quite a bit slower than a leather simulation because it's just more work for the solver to do. Now we have a new scene in Maya, and let's look towards the bottom at the timeline. I've blurred out the rest so we can focus on the timeline. Our Maya scene is set to 30 FPS, which you can see towards the bottom right corner, which means that 1 second is split up into 30 frames. We have 60 frames in our timeline, which means we have 2 seconds being simulated here. 2 times 30. Now, how do iterations and subdivisions come into effect here? Let's summarize again. Iterations is the number of iterations per simulation subdivision. Iterations control the conversions, so the more iterations, the better the conversions towards the problem. Subdivisions, they're the number of subdivisions per frame. So a simulation time step, which means the time step of the internal carbon solver, is 1 over frames per second times subdivisions. So if we have 30 FPS in our timeline and 20 subdivisions, that makes it 1 over 600, so our simulation is 600 Hertz. If you have small or thin objects and fast motion, you need higher subdivisions to better sample the time to avoid objects interpenetrating. The number of subdivisions is also very important to capture fast oscillations. Time sampling must be smaller than the frequency of the oscillations, and the number of subdivisions is your friend in this case too. So in summary, any simulation error is relative to the simulation time step. Let's visualize this with an example. Let's say we have 10 iterations and 20 subdivisions, and here we have our scene again with 30 FPS. So 1 second split into 30 frames, and then each frame has 20 subdivisions, and then each subdivision has 1 collision detection beginning and 10 iterations. If you add this all up, it means 1 frame has 20 collision detections and 200 iterations. And our simulation runs internally at 20 times 30 Hz, so 20 subdivisions times 30 FPS in our timeline. Now you might wonder, is it better to crank up iterations or subdivisions? Generally, it's better to increase subdivisions first and then iterations once you max out your subdivisions, which is usually around 300. We do not recommend going above 300 subdivisions. Why is it better to increase subdivisions first? Well, increasing subdivisions, as you can tell, adds more collision detection. So you get better sampling of your time and your error is smaller. It helps you deal with fast motion and thin geometry. In this scene, if you had 20 iterations and 10 subdivisions, you would still end up with 200 iterations per frame, but only 10 collision detections. So that's only half the collision detections, which can be a problem with fast motion and thin geometry. Length scale. Per default, Carbon assumes that your scene units are in meters. But often you get assets and scenes where your units are meters, centimeters, or even millimeters. Now, how do you tell Carbon that one scene unit does not actually represent 1 meter? It's via the length scale parameter. If your scene unit is, for example, a centimeter, so 1/100th of a meter, you set this one to 0.01, and then it behaves accordingly. Let me show you an example. So I have a cloth here, which is 1 by 1 scene units, and let's assume this is 1 by 1 meters. So length scale stays by 1, and I'm going to reset the simulation, and let's run this now. And you can see our cloth is falling. Now, if we had our length scale set to something wrong, for example 100, saying that every unit in here corresponds to 100 meters in real life. If I reset the simulation now, you can see that it actually falls much slower. The gravity is the same, minus 9.81 meters per second square. So if this is 100 per scene unit, then if it drops by 1 in this, that's actually 100 meters. So obviously you need more frames for it to drop 100 meters in here. And similarly, if I change this to 0.01, saying that 1 scene unit here corresponds to 1 centimeter, you will see this fall much more rapidly. Reset and go ahead. This is now obviously a much larger gap because 1 scene unit only corresponds to 1 centimeter. When I set up a new carbon simulation, the first thing I do is set the length scale. I look at my assets and figure out if it's meters, centimeters, or millimeters, or whatever other unit you might have, and then set the length scale so that I know my simulation from here on out is set up correctly. Here's another example where I can demonstrate the impact of length scale. Our avatar is about 170 to 180 scene units tall, so that's in centimeters. Our length scale therefore is correctly set to 0.01, so 100th of a meter is 1 centimeter. Let me reset the simulation and run a few frames. You can see that it behaves as you would expect, an avatar with a tank top and a skirt. Now if I had forgotten to change the length scale and kept it at 1, the carbon would assume that every unit in here corresponds to 1 meter. So this one would be about 170 to 180 meters tall, and the impact on gravity of your cloth would be very different, which you can see when I run it now. Your garments almost look like they're floating, and this is obviously very wrong. So usually when you have your length scale set incorrectly, it's quite easy to spot because everything looks way heavier than it needs to be, or it looks way lighter than it needs to be. Sometimes this can also be used as a special effect. So let's go back to 0.01. Let me reset the simulation and run this again. And you can see maybe these garments feel a little bit too lively, and you're doing a shot for, let's say, a kid's movie where everything's supposed to look a bit more leathery and a bit more subdued. What you can do is then reduce the length scale a little bit more, which will make everything look a bit heavier. So I'm going to over-exaggerate this, add another 0, reset the simulation, and you can see that this should now look much heavier. And that's less lively. So it's a little bit of a hack, but sometimes it can be quite useful. Let's talk about timescale and time warp. They're similar parameters, but there are some differences. Timescale is a ratio which defines the value of the time in the scene. Use 1 for 1 second per unit and 0.001 for 1 millisecond per unit, etc. The timescale works the same way as the length scale by applying to parameters that are time dependent, such as acceleration of gravity, velocities, or stiffness. You should not animate this parameter and use it as a correction like the length scale. For example, if you set it to 10, then Carbon simulates each frame assuming they span 10 times the length, as it would with just a timescale set to 1. Let me demonstrate this to you. Let's reset the simulation, and we have a timescale of 1, and I'm just gonna run a few steps in the simulation, and we can see the cloth is just falling over the sphere. Now, if I set the timescale to 10, Carbon will treat each frame as basically 10 frames, so 10 times as fast. Let's have a look. 1, 2, and here we are. Now, in order to compare this, we can take screenshots. So here we are at frame 2 for this. Let me do a screenshot. Just delete this, and let's call this 2. Save 2. And then let's go back 1 frame. And here let's take another duplicate and call this save 1. So when we go back now to the simulation and reset this to 1, for example, reset the simulation, and I have to go 10 frames to get to here and 20 frames to get to here. So let's have a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at frame 11, we match this. Then if we go up to frame 21, we should roughly match the other one. There we go. Obviously, it's not precisely the same simulation as the parameters are slightly different, but you can see that it's a factor of 10. Similarly, you can do this other way around. So if you want to slow down the simulation, you can set a timescale of 0.1, for example, and now we're 10 times slower. We'd have to go to frame 101 to get the same result. So currently the timeline only goes till 100, so let's change it to 101. And here we are matching at frame 101. 101. Perfect. I hope this makes sense. So now you might wonder, why not just change the gravity in here? Well, this does not only affect gravity, but everything that has to do with acceleration or velocities. So you would do this when the animation is coming in at a different frame rate than what the timeline is. For example, your timeline is 24 FPS or 30 FPS here, but your animation was done in 60, and now it basically plays twice as fast in here. So then you could use your timescale to set it to 2 to make the simulation understand that your animation is actually twice as fast. Let me show you another example. All right, what have we got here? Here we've got a cloth on a block, and what happens? Well, we're just animating the block to go here from frame 10 to frame 90. So the first 10 frames it just settles, and then over the next 80 frames from 10 to 90, this thing moves over here. And the simulation runs with default parameters. If you have a look at this, timescale of 1. So now what happens, as I said, if your animation comes in too fast? Well, I can change this quickly. Let's go to the cube, go to my animation. And instead of going over 80 frames from a value of 0 to 10 in X, let's do it 4 times as fast, so over 20 frames. So we change the 90 to 30. Now we reset the simulation, and if you just run this, you can see our cloth is falling off. What we need to do is change our timescale. We made it 4 times as fast, so set the timescale to 4. Reset the simulation. What happens now? Here we go. And it keeps track because Carbon is in sync with the animation. Now this covers timescale. What about time warp? Time warp is a multiplier of the time step, and it changes the meaning of the elapsed time by contraction or dilation, while timescale is a ratio which defines the value of the time on the scene. So in practice, what is the difference? The difference is you should not animate your timescale, but time warp should be used when you go in and out of slow motion. So this is your classic slow motion effect, like in the Matrix, when a scene is at normal speed and then the character simulation slows down to a very slow motion shot, for example, ducking from a bullet. Time warp allows you to slow down your simulation in the same way your animation is slowed down, so that you get consistent behavior. Let me open a scene from the documentation to show you what I mean. This is an example from the documentation, and I've deactivated the timescale example in here, so ignore this, and the timescale example would be in between. I just want to look at normal simulation and time warp. So let me open the time warp simulation. We've animated the time warp along with the animation. Let me just play it once. All right, that was probably too fast. Let's go through it. We have a cylinder that spins and cloth on it that's bound in the center. First it's normal speed, and then it slows down. As it slows down, our normal simulation without time warp or timescale set still has momentum in the cloth, and it then basically slams against our actor and is forced to slow down. Meanwhile, our time warp is a much smoother behavior because we try to animate the time warp parameter in alignment with the slowdown of the animation, so we don't get this fast slamming down here and here. Then this just keeps moving fast, and since we've animated this and saying this is actually a slow motion, we also don't get the effect of gravity. A normal scene here, we have the cloth just fall down under gravity as it would, but since this one is a time warp, here we have 0.2, so 5 times slower, the gravity has a lower effect, and this obviously falls slower as well. And here we go, and then we're gonna go to normal speed, and now starting at frame 420, our cylinder is spinning 4 times as fast. We immediately see the effect on our default simulation without time warp setting. The cloth starts stretching under the speed from the spinning. And then we're gonna slow down again, and our normal one has a heavy effect to the drastic slowdown, and it basically starts slamming, while our time warp is a much lesser effect, and it settles really nicely back in. In summary, use timescale when you want to change the time effect for the whole timeline and you're not planning to animate it. If you're not animating time warp, it basically has the same effect as the scale. But whenever you're planning on animating, use time warp, please, not timescale. Next up, maximum linear motion. Maximum linear motion is set per time step. It is a speed limiter and the maximum displacement per subdivision that the Carbon simulation will allow on anything. It is a useful feature to avoid objects disappearing into the horizon when something blows up, or keep high speeds under tight control. In practice, what does this mean? Well, maximum linear motion is set to 0.5 and we have 30 subdivisions. 0.5 times 30 means 15 scene units is what's allowed per step now. If I reset my simulation and I'm in centimeters here, this sphere is at -100, so about 100 scene units minus subtracting the radius between the cloth and the sphere. And it takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it takes about 11 steps for it to reach. On average, that means under 10 scene units for it to reach. So maximum linear motion does not limit my motion in here. But if I reduce this now to, let's say, another factor of 10, 0.05, reset the simulation, you will now see this kick in, and my cloth will move much slower and the gravity will not have full effect. So we get a speed limiter on this. It is very useful when you have fast scenes where things might blow up or move far away, but often it can have the unintentional effect of slowing you down. So what I like to do in a lot of scenes is to just increase this to something quite ridiculously large so it doesn't stop anything that I don't want to be stopped. Damping. This is a damping force coefficient. It behaves similar to having a uniform flow in the scene. It just dampens all behavior and removes some small oscillations and wiggles when used sparingly. Normally we recommend using a factor of 0.1 or maybe even 0.5 if you want to do quite a lot of damping. In the scene you won't see much of a difference because it's already pretty calm, but it's gonna reduce some of the swinging here. Obviously, if I take this way too far up, let's say to 100, you're gonna see a heavy impact like this, but you wouldn't use it this heavily. Generally, 0.1, 0.2, 0.5 are fine. The one thing to keep in mind is that it affects all objects in the scene, so all of your cloths or rigid bodies all will be damped equally. This is often not what you want to do. You normally want to control the behavior of each object separately. So what you can do then here is, for example, go to the carbon cloth, go to the viscous damping parameter, which is right up here, and then change this per cloth, so you can control it in a more targeted manner. Sometimes you find yourself in a situation where your simulation blows up. This could be from over constraints or maybe collision trapping the cloth and the cloth blowing up. At this point, things start slowing down and you can see that your cloth is all over the place and you want to interrupt the simulation. What you can do is hold the escape key and keep it pressed. Carbon will under the hood automatically check the physical state of your escape key, and once it detects that the escape key is pressed, it will stop the simulation. So this is a way to get out of it. But you cannot always be on your machine, or sometimes you run on the farm and you cannot see any results until it's ran through. Now, if your simulation starts blowing up, it can slow down the whole farm and crash mine. We have a parameter called panic time. This is a safety feature. Panic time is the valid simulation subdivision time threshold in seconds. If a subdivision takes longer to simulate, then the simulation is interrupted. So it allows you to recover the session in case of heavy geometry corruption as alternative to the escape key. You can set it to 0 to completely disable it, or just use a very large number as a safety buffer. Let me show you what this means in practice. Here we have a simulation, and let me reset this, and you can see we have 100 subdivisions. I'm going to run this now. Okay, let's bring up the script editor. Here's the script editor, and if you look at the frames, we're here just at over 100 milliseconds and just under 100 milliseconds per frame. So 100 milliseconds per frame, and we have 100 subdivisions, which means each subdivision, if we assume they're about equal in time throughout a frame, takes roughly 1 millisecond. Which means if we set our panic time to 1 millisecond, 0.001, it will trigger if a subdivision takes longer than 1 millisecond. Let's reset the simulation and run it. And here we are. Now it has triggered. Well, let's have a look where it triggered. Well, it triggered the last frame, took over 100 milliseconds. So on average, a substep took around 1 millisecond and passed this threshold. This also shows you that it can be a little bit tricky to set the panic time just based on the first couple of frames, because often in the beginning you're in a configuration where there's not a lot of collision going on and your frame time is a bit faster. Once you start simulating and you get collision, like the cloth hitting the sphere more and more, we're going to add more time to the collide. And as you see, this goes up, the whole frame time goes up, and then you get over the threshold. I'm going to put this aside now, and that's tenfold increase the panic time, and I would expect it not to trigger anymore. And here we go, our simulation seems to run through fine, we got no problems, but our panic time is still there. So if any of the frames now takes about 10 times as it would normally, then panic time will trigger. And this is how you would tune your safety feature. Also keep in mind that when you tune it on your machine might be faster or slower than other machines. So if you have a fast desktop and you tune it that it just barely is larger than your frame time, so it doesn't quite trigger yet, but then you put it on the farm and the farm maybe has a slower machine and then it triggers on the farm. That's why I would give it a generous gap, maybe 10 times, because I would assume your farm is probably not 10 times slower than your local machine. Next up, simulation space. If you click this, you should get a gizmo where the simulation is located. Now it might be too small, so we might have to bring up the gizmo scale. Let me increase this, and here it is actually. Here's our gizmo, and this is where is our simulation located. Well, our simulation is located at position 0 in no rotation, and there's also no transform source. This just gives an indication where the simulation is. This can be quite useful when you have very fast moving animation, for example Superman. So you can make your simulation move along with the animated character so the cloth is not being dragged behind by that speed. Let me bring up an example. Here's the example simulation space and goal posing MB file from our documentation. What's happening is here we have a sphere that moves left and right very fast, and the camera is actually moving along with it, so you won't really see the effect right now. Let me first simulate. Our cloth is goalpost to this grid, so here it's very strict, and here it is obviously very dynamic, very loose. Now, you might not see that anything is actually moving much, but let me change the camera and actually disconnect the connection to the animated sphere. So now the camera is still. And you can see the sphere is moving left and right very fast. If we did not provide a simulation space to the carbon simulation, what would happen? Well, our cloth would drag behind. So as you can see right now, it is acting like there's no left and right motion and it's just going up and down with the goal posing. But if I remove the simulation space, set the transform source to none, reset the simulation, now we're back to basically no simulation space. And once I run the simulation, you see what happens. Well, our cloth gets dragged behind like crazy and it can't follow up with the fast motion, and it's not really what we want. So yeah, so this can be used for Supermans, or if you have fast cars and, for example, flags on cars or ships or things like that, and you do not want them to be affected by the overall motion, you just parent your simulation under one of those fast objects, and then that motion will basically be cancelled out. Next up, Detangle. Detangle is a relatively new feature that was introduced just before 3.0, and it is a live detangling. Detangle consists of multiple pipelines, which can either be all turned on, or you can customize which ones you want on. What do they mean? S means soft, which stands for cloth or a morph, and A for actor, which is an actor or a collider, and R stands for rigid. So you can turn off soft self-collision, detangle, soft versus soft, so one cloth with another, collider versus soft, or rigid versus a cloth, rigid versus soft. Per default, all is turned on, and I would recommend leaving this on. It's really powerful and makes your simulation setup much more stable and allows you to get away with a lot more issues that normally we would have struggled to resolve. Also, I'm linking to a video which you can see on the screen right now, which explains some more of this. Next section is live simulation. This basically allows you to run a live simulation almost like game style in your viewport using the carbon simulation. We have a couple videos that explain this in depth, and they should pop up on your screen now. I recommend you watch those, and they give you a lot more information that I could cover in this video right now. Beta features tend to be some small additions for customers or features we're using internally. Now, display layer support. This allows integration into the layer editor, which you see down here. Next up, color outliner. So when you have an object, for example, a carbon cloth, and I set it to activate 0, reset the simulation, now this is being colored yellow. If I turn this off and reset the simulation, you will not see this yellow color on this anymore. Also, when you have a cloth, for example, and net to not provide a start mesh, so there's an error on the actual cloth on a simulation node. When I color the outliner, let me turn this on again and reset, it shows red. If I do not have color outliner ticked, it does not show. So if you do not like the colors, you can turn it off here, but generally I recommend keeping it on because it's easy then to spot if there's an error on any nodes, or if there's a warning on nodes, for example, like deactivated, which is marked in yellow. NMRB export. NMRB is a custom file format that we use internally for debugging and sharing data between this and our internal testbed. You can ignore this as you probably won't need this. Next up, About section. This gives you information just about our copyright and our plugin version. I'm currently using this beta version in preparation for the upcoming release of our plugin. Then you have license status. To know more about the license status, I would recommend reading through the documentation where we explain more how this works, but basically there are two licenses in here. There's simulation and there's cloth license. And if the license is successfully checked out, this says license and it says licensing successful. If there are any issues, you should see the bug messages here. Well, I hope this all makes sense and helps you understand the carbon simulation node some more. Thank you for watching.